Hello everyone. Today we are to start with the topic combination of resistances. In the previous lecture we have already studied about our factors. Along with that we have studied about how our current behave at a node point where its path gets divided. There we have discussed that incoming current is equal to the outgoing current. Okay. Now let's talk about combination. If we are given any two resistances means any kind of wire or heating coil or any kind of bulb. If you are given two bulbs, how you should combine them? There are two methods. Either they are combined in series form, that is, suppose there are two persons standing over here. These are two persons. How these two persons should form a bond? Either by attaching the left hand of a person with the right hand of another person. This is known as series combination. Or simply make two persons stand one after the other, and then left hand of one person connected to the left hand of another and right hand of this person connected to the right hand of another person. Right? This is known as parallel combination. Let's see now how resistance would look like. Let's suppose here we shall be showing our series combination. Here we shall be talking about our parallel combination. Okay. Let's suppose these are our two resistances. We have already studied in our 8th standard how our resistances look like in a circuit. Let's suppose these two resistances are connected through a battery. Let's suppose the total potential of the battery is V. This is the series combination, that is, left of one is connected to the right of another. Let's talk about parallel combination. Making two stand one after the another so that left of one is connected to the left of second and right of one is connected to the right of the second. Then we are going to connect it through a battery. Again of potential difference V. Okay. Let's suppose from here I current is flowing. Let's suppose from here also I current is flowing. Okay. If you must have observed in these two cases, current in the series combination, the path for the current is from here to here to here. This is whole path for the current. There are not any diversions, right? There are not any node points, alright? So whatever the current is here, that whole current would flow through here, through this resistor R1. Again that whole current would flow through here, through this resistance R2. Then again comes back here, this again the same current, and comes to this negative terminal of our battery. Since our battery is providing the potential difference. Okay. So can we say that negative terminal is at 0 and positive is at V? Then again the potential difference will be V minus 0, that is V. If the negative be at minus V and this positive terminal is at 0, then again our potential difference would be higher minus lower one. Again it would be V. If this is 2V, this is V, then again potential difference is V. So for our convenience, we are taking the first case where we are considering negative terminal to be at 0 potential and positive terminal to be at V. Okay. If this point is at 0 potential, throughout the wire, Can you find any of the device which uses this potential difference or which is using this energy? No. That means this point will again be at zero potential. If this is at V potential, so throughout this path up till this point, we do not find anything that could use up this energy, right? If nothing uses this energy, then again this part will be at V potential. Now, from V potential, this resistor is using up this current. That means this resistor is using up some energy from the battery. If this is using some electrical energy, that means there must be some potential drop. Let's say at this point our potential drop is Vc. Okay, now let us see if we just attach our R1 resistance through a voltmeter showing voltage V1 and our R2 resistance through a voltmeter showing potential difference V2. So what do we have? This total V, that is this total potential energy, is being divided into these two, V1 and V2. So V equals to V1 plus V2. Okay, let's see what V1 would be. V1 equals to V minus Vc, which is basically equal to current into our resistance by our first Ohm's law. Okay. Then again V2 equals to Vc minus 0. This is our potential drop, which is basically equal to, since the same current flows through R2, this is equal to R2. If we just add up these two equations, what do we have? V1 plus V2 equals to V minus Vc plus Vc minus 0. Vc gets cancelled out. What do we have? V minus 0, that is V, equals to I into R1 plus R2. Okay. Here, the total potential difference is equal to the total current in the circuit multiplied by the total resistance of the circuit. We are taking total resistance to be Req, that is R equivalent. If we just substitute this in our first equation, what do we have? The result of our series combination as I into R equivalent equals to I into R1 plus R2, which gives our R equivalent equals to R1 plus R2. This is the result of our series combination. Okay. Similarly, let's find out the result for our parallel combination. In parallel combination, since at this point we are finding a node from where we have got a diversion in our path. So, current through here is divided into two parts, I1 and I2. Okay. If this is 0, this is V, then this point will be 0 and this point will be at V potential, right? So, potential difference across both of these resistors will be same, equal to V. Okay. Let's see. If V equals to IR, then I must be equal to V upon R, right? Let's see. I incoming equals to I out. So, I incoming at this node is I and I out is I1 plus I2. Okay. I1 is basically equal to V upon R1 from our next equation. I2 is equal to V upon R2. If we combine these two equations, what do we have? I1 plus I2, which is basically what? I equals to V upon R1 plus V upon R2 Okay, again with this, by this law, V equals to I into R equivalent. If V equals to I into R equivalent, then I will be equal to V upon R equivalent. Let us use this to get our result for our parallel combination. What our result would be? V upon R equivalent is equal to V upon R1 plus V upon R2. I have taken V as common. It gets cancelled out. So the result for our parallel combination is 1 upon R1 plus 1 upon R2. Okay. Now that we have got our results for series combination and parallel combination, so let's see what conclusion could we draw from these results. If we just look over here, R equivalent is R1 plus R2. Let's take some hypothetical values. Let's suppose R1 is equal to 1 ohm and R2 is equal to 2 ohm. Okay, so in series combination, R equivalent is equal to 1 plus 2, R1 plus R2, that is 3 ohm. This is the equivalent resistance in series combination. In our parallel combination, 1 by R equals to 1 by R1 plus 1 by R2. Let us solve it a little bit. 1 by R equivalent equals to 1 by R1 plus 1 by R2. What do we have? 3 by 2. So R equivalent is equal to 2 by 3, which is equal to 0.67 ohms. This is the equivalent resistance in our parallel combination. So can you find some pattern over here? What's the pattern? That in series combination, the equivalent resistance is greater than the maximum individual resistance. See, in 1 and 2 ohm, maximum resistance is 2, minimum is 1. R equivalent in series combination is greater than individual maximum resistance. This is always there. In parallel combination, R equivalent equals to 0.67, which is even lesser than our minimum resistance. This was 1 ohm, this was 2 ohm, right? So in parallel combination, our R equivalent is less than R individual minimum resistance. This is our first conclusion. Next conclusion. In our series combination, current remains the same, right? I equals to same. But in our parallel combination, what remains same? V equals to same. Okay. Then in our series combination, voltage is divided in V1 and V2. So this ratio of potential difference is equal to V1 is IR1, V2 is IR2. So this is equal to the direct ratio of our resistances. In our parallel combination, I equals to V upon R1, I1 equals to V upon R1, I2 equals to V upon R2. So our current, I equals to I1 plus I2. So these two current gets divided into inverse ratio of our resistances. These are the three most important conclusions drawn from our combination of resistances, that is in series combination and in our parallel combination. Okay, using these conclusions, there are some applications of parallel combination of resistances. One most important application is that our parallel combination is used in our domestic circuits. Now, why is it that they are only used in our domestic circuit? Because if by chance one of your bulb stops working, still the circuit is complete. The current could easily flow through the second bulb. That means whenever one electrical appliance is damaged, still your other appliances work. That is the main advantage of your parallel combination. If we come to our series combination, if one damages, that means what it does, it opens up our circuit. And once the circuit is open, then current stops flowing, right? So series combination is not used in our household or domestic circuits. But have you ever seen the practical application of series combination? Yes, our Diwali lights. The LEDs that we use for decorations of our homes during Diwali, they use series combination. They are small lights of very least resistances. Okay. Alright, now let us solve a few questions based on combination of resistances, how we are going to implement these conclusions in our questions. Okay, let us just write down our conclusions over here. Conclusions for series combination. First conclusion, I remain same. Second conclusion, R equivalent equals to R1 plus R2 and so on. Third conclusion, V1 ratio V2 is direct ratio of resistances. Fourth conclusion, our R equivalent is greater than R individual maximum resistor. Coming to our parallel combination. First, V remain same. Second, 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 and so on. Number third, I1 ratio I2 is equal to what? Inverse ratio of resistances. Fourth conclusion, our R equivalent value is less than minimum individual resistor. Alright. This was for our parallel combination. This was for our series combination. Okay. Let's solve a question. Let's start with some basic questions. Let's suppose we are given 3 resistors, 1 ohm, 2 ohm and 3 ohm connected to a 12 volt battery. We need to find out the current through the circuit. Number second, we need to find out the equivalent resistance of the circuit. Okay. For the current through the circuit, we need what? Equivalent resistance already. So R equivalent in our series combination equals to sum of all the resistors. 1 plus 2 plus 3, that is 6 ohm. Since we have our equivalent resistance, now we can easily find out the current through our circuit. So current would be what? V upon R equivalent, which is basically equal to 12 upon 6, that is 2 amperes. So our current comes out to be 2 amperes. Now since current equals to 2 amperes, so if there happens to be a question where they ask you what would be the current through this ammeter between 2 ohm and 3 ohm, then definitely since this is a series combination, our current remains same. So current through this ammeter will again be 2 amperes. Alright. Let's come to another type of question. Okay, let's take one more part. Suppose this is A part. In both the parts, we are to find out the same. Suppose in B part, we have two resistors, one 3 ohm, another one 6 ohm. We are to find out the equivalent resistance of the circuit. Let's suppose this is 4 volt. Okay. This is I1, this is I2. Alright, let us try to solve it over here. 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2, which comes out to be so R equivalent is equal to what? 2 ohm. If R equivalent is equal to 2 ohm, then current through the circuit, total current would be V upon R equivalent. It is 4 upon 2 equals to 2 ampere. This is our total current. Okay. Now, since our total current is 2 ampere, let's see how much current is flowing through 3 ohm resistor and how much current is flowing through 6 ohm resistor. We have got two equations, I1 plus I2 equals to I, that is 2 ampere. Second equation comes out to be that I1 ratio I2 equals to inverse ratio of resistances 1 by R1 ratio 1 by R2, that is R2 upon R1. Alright, so I1 upon I2 becomes 6 upon 3, that is 2. So from here we have got I1 equals to 2I2. If we just substitute it in our equation 1, what do we have? 2I2 plus I2 equals to 2. So 3I2 equals to 2. So I2 equals to 2 upon 3 ampere. Then I1 becomes 2I2, that is 4 by 3 amperes. To check the validity of our answers, add these two. 2 by 3 plus 4 by 3 becomes 6 by 3. If we just solve it, we already get 2 ampere, that is I. That means our solution is apt. Okay.